Welcome to the Deep Dive. We're the show that tries to help you cut through the noise and really get to grips with complex topics.
Yeah, wading through information overload. We've all been there.
Definitely. And, large language models, LLMs, they face a similar problem, right?
Yeah.
How do you process just vast amounts of text efficiently?
Exactly. And that's what brings us to today's topic, retention. It's this really interesting new development from researchers at Apple.
Retention. Okay.
Yeah.
So the goal is making LLMs smarter, faster, handling more information.
Pretty much, making them better at processing longer contexts without, getting completely bogged down. So our mission today is basically to give you a shortcut.
A shortcut through the papers?
Yeah, drawing on the academic work, the study guides. We want to unpack how retention actually works, how it redefines efficiency and performance, and crucially, why the technical ideas behind it are so significant.
Think of this as your express lane to those aha moments, understanding how these models really tick and why this specific breakthrough matters for AI's future.
Right. But to really get why retention is cool, we first need to talk about the problem it solves, the bottleneck.
Okay, let's set the stage. Why do LLMs struggle with long texts in the first place?
Well, fundamentally, most LLMs are built on transformer architectures. Super powerful, yes, but they hit this major wall with long sequences. It's called the quadratic scaling problem.
Quadratic scaling. Okay, break that down. What does that mean practically? What's a bottleneck?
Sure. So in standard full attention, every single bit of information, every token needs to look back and consider every other previous token.
Every single one.
Every single one. So as the text length, the context length grows, the amount of computation and memory needed just explodes quadratically.
Wow, okay.
A big part of this is something called the KV cache. Think of it as the model's working memory during inference.
Right, I've heard of that.
Its size grows linearly with the sequence length. So longer text means a bigger cache, which leads to really, really heavy memory use. It just becomes impractical fast.
So, okay, quadratic compute, linear memory growth with the KV cache. That sounds like a major headache for long documents or conversations. What was the first stab at fixing this?
Well, the most straightforward early attempt was sliding window attention, or SWA.
SWA. Got it.
It was a pretty clever partial fix. The idea was, okay, let's not look at everything. Let's just limit attention to a fixed window of the most recent tokens.
Like only focusing on the last few things someone said.
Exactly. And the big win there was constant memory use during decoding. That was huge for efficiency.
But I sense a but coming.
Oh, yeah. It immediately created new issues, specifically this inherent Pareto tradeoff.
The Pareto tradeoff
between
model capacity and efficiency, right? That's what the retention paper really focuses on.
Precisely. With SWA, you're forced into this difficult choice.
Okay, so what are the horns of that dilemma? Larger window versus smaller window.
If you go for a large window, say 4996 tokens, like in Mistral or some Gemma models, you keep good performance generally. But you lose a lot of the efficiency benefits, especially for shorter tasks.
How so?
Well, think about a 12 billion parameter model with a 4K window. If you're only processing, say, 1,000 tokens, you're still allocating memory for that full 4K KV cache.
Ah, I see. So you get basically no KV cache savings unless you're actually using that huge context. You're still carrying that memory baggage.
Exactly. Minimal efficiency gains in many common scenarios.
Okay, so that's the downside of big windows. What if you swing the other way? Make the window really small for maximum efficiency.
Then you risk performance degradation pretty significantly sometimes.
Why? Because it forgets too much.
Essentially, yes. Local attention, by design, completely disregards tokens outside its little window. It's like having a conversation but only remembering the last minute. You lose all the crucial earlier points.
Right. And that heuristic people, quote, number of layers times window size should cover the context length. That's not always enough.
It's often inadequate. It's just a rough guide and doesn't really capture the need for accessing specific, important information from way back. It's a pretty blunt instrument, frankly.
So SWA was a step, but it left this fundamental tension unresolved. Either performance or efficiency suffers somewhere.
Correct. And this is where retention comes in. Its goal isn't just a small improvement. It's about fundamentally shifting that Pareto frontier.
Enabling good performance with much smaller window sizes.
That's the key idea, getting the best of both worlds, essentially.
Okay, so we've got the problem clear. Sezway's trade-off. How does retention actually break that trade-off? What's the secret sauce?
The core innovation is its hybrid approach. It's really clever. It combines the standard sliding window attention SWA for handling the immediate local context.
The stuff right nearby.
Right. But then it adds this completely new component called residual linear attention, or RLA.
Residual linear attention,
Sure.
RLA.
And RLA's job is specifically to capture information from those important tokens outside this SWA window, the older stuff.
Okay, so if SWA is the short-term focused attention, RLA is what?
Yeah.
Like a long-term memory summary?
That's a great analogy. Think of SWA as focusing on the last few sentences, but RLA is like this highly efficient background system that recalls the gist of everything said much earlier.
Without needing to store every single word for the beginning.
Exactly. It summarizes and brings forward the relevant long-range context that SWA would otherwise just drop.
That sounds incredibly useful.
Yeah.
Okay, let's dive into RLA itself. This is the core academic bit, right? How does it technically overcome SWA's limitation?
Yeah, this is where it gets really interesting mechanically. So unlike standard linear attention methods that might read from the current hidden state, RLA is designed differently. Its output, how it figures out what to saw, comes from looking at a state that's specifically before the current sliding window starts.
So it's deliberately looking past the SWA window.
Precisely. It's engineered to target and summarize context from tokens beyond that sliding window, the stuff SWA ignores. But the real kicker, the academic novelty, is its recurrent nature.
Recurrent, meaning it builds on itself over time.
Yes. And this is crucial for two reasons. One, it preserves that constant memory property during decoding that SWA gives us, super important for efficiency.
Keeps the memory usage flat.
Got it. And two, this recurrent aspect lessens the model's over-reliance on just knowing the position of words, which is what positional embeddings track.
Less reliance on positional embeddings.
Yeah.
What does that mean for you, the listener, in practice? Better understanding of long texts.
It means the model gets much better at generalizing to sequences longer than what it was trained on. Significantly better. It's called zero-shot length generalization.
So it can handle unexpectedly long inputs without extra training.
Markedly better, yes. Because it's not just relying on learned positions that might run out. It has this mechanism, RLA, to actively compress and carry forward older context. That's a really significant contribution to handling long sequences efficiently.
That is clever. But adding a whole new RLA component, doesn't that mean more parameters, more complexity, bigger model size?
And this is maybe the most elegant part of the design. You think so, right? But amazingly, retention introduces 0 additional parameters compared to a standard SWA module.
0. How?
It simply shares all the parameters. The query, key, value, output, projection matrices, all those learned parts are used by both the SWA calculation and the RLA calculation.
Whoa. Okay, that is elegant.
It's a huge advantage. Compare that to other hybrid approaches like, say, HIMBA, which needed separate parameter sets for their different components.
And having separate sets can cause problems.
It can limit the capacity available for other important parts of the model, like the feed-forward layers, especially when you try to scale the model up. Retention avoids that entirely. Parameter sharing makes it much cleaner and more scalable.
So SWA does its local thing, RLA does its long-range summary using the same machinery, essentially. How are their outputs combined?
They take the output from SWA and the output from RLA, normalize them using RMS norm, and then simply add them together, a straightforward sum.
Simple addition, okay. And I remember reading they found a specific mathematical function, a softmax-based feature map, worked best inside RLA.
That's right. Ablation studies, where they tested different components, showed that this specific feature map gave the best performance for RLA. So the exact math inside RLA matters too. It's not just the concept.
So it's a clever architecture, very parameter efficient. But theory is one thing. Making it work fast in practice often needs smart engineering, right? Did they do anything special there?
Absolutely. The practical success isn't just the architecture. It's also about optimizing the implementation, particularly the kernel design.
Kernels, the
Okay.
low-level code that runs on the hardware.
Exactly. They use techniques like fused operations. This means combining multiple computational steps, like calculating that RLA feature map into a single kernel.
Why fuse them?
It drastically reduces memory input-output costs. Instead of calculating something, writing it to memory, reading it back for the next step, you do it all at once. Less data shuffling means more speed. It avoids intermediate memory bottlenecks.
Makes sense. Keep the data close to the computation. What about this flexible state saving for training?
Yeah, that's another smart optimization for training the model. Training often happens in chunks. Now, You could save the model state after every single chunk, but that's a lot of memory writes.
Or you could recompute everything from scratch each time.
Right, but that's a lot of wasted computation.
Mhm.
So they found a middle ground. They saved the full state only every M chunks, let's say every 8 or 16 chunks.
Okay.
And for the intermediate steps within those M chunks, they just recompute the necessary states on the fly, keeping it on the chip's faster memory.
So it balances memory saving versus recomputation cost.
Exactly. It's a hybrid approach that balances memory, I/O, and compute, and it gives compilers more room to optimize the whole process. It's about finding that sweet spot for training efficiency.
Okay. Smart architecture, smart engineering. Now the big question, the so what? Does it actually deliver? How does retention perform in practice? Does it really shift that Pareto frontier we talked about?
And the results are, frankly, pretty stunning. This is where it gets really exciting. Retention, using a window size of just 512 tokens.
512, that's tiny compared to the 4096 we mentioned earlier.
Exactly. Retention with only 512 tokens consistently matches or even beats the performance of full attention models on standard benchmarks like MMLU, ARC, HelloSwag. The list goes on.
Wow. So you get the efficiency of a tiny window, but the performance of looking at everything.
That's the breakthrough. It really delivers on that promise. They showed this clearly in experiments with 3 billion and 12 billion parameter models. Retention 512 outperformed standard SWA models that were using much larger windows, like 124 or even 2048 tokens.
That's a monumental practical achievement. Huge reduction in that active window needed.
It really is. And it's not just standard benchmarks. They also tested long context generalization using the ruler benchmark.
And how did it do there? Handling text longer than its training.
It showed superior zero-shot generalization, meaning the retention models performed well beyond their 4K training context length, while other models often started to fail significantly.
And there was that interesting finding about smaller windows sometimes being better for generalization.
Yeah, that was fascinating. They found that smaller window sizes, like 512, could actually generalize better to very long sequences than slightly larger SWA windows.
Why would that be? Seems counterintuitive.
The hypothesis is that the smaller window puts more pressure on the attention mechanism during pre-training. It forces the model to learn more robust, generalizable patterns to capture context, rather than just relying on a large, explicit window. The RLA component likely plays a big role here, too.
Fascinating. Okay, performance is great, generalization is strong. What about the bottom line? Efficiency, training, and inference speed.
So for training, despite the added complexity of the hybrid approach, they managed to keep training speeds comparable to the state-of-the-art SQLA models. No major slowdown there.
Good. But inference is often where the rubber meets the road for practical use.
And that's where retention really shines. Because of the small window and the constant memory usage from Swarla, the inference gains are significant. Theoretically, they project step time speedups during decoding generating text of up to around 60% as you process more requests in parallel, like with larger batch sizes.
60% faster text generation.
Potentially, yes. Driven largely by those massive savings in the KV cache size thanks to the small window. That directly impacts how fast these models can respond in real applications.
And just to reiterate, other attempts to combine SOA and linear attention existed, but retention is the one that really closed the gap with full attention performance.
Correct. That's a key differentiator. Previous hybrids often didn't quite reach parity with full attention across the board. Retention seems to have successfully bridged that gap, making it a uniquely effective approach.
Okay, so stepping back a bit, where does retention fit in the bigger picture? There are other ways people try to make attention more efficient, right? Like sparse attention.
Absolutely. It fits into this family of constant memory models and their hybrids. We've seen other interesting approaches, like Gemma models alternating SUA with some global attention layers, or Jamba mixing SUA with Mamba, another recurrent architecture.
How does retention compare?
It stands out mainly for its parameter efficiency, that zero extra parameter trick, and achieving that performance parity with full attention, which, as we said, wasn't always the case for earlier hybrids like Himba. It's also distinct from sparse attention models.
How are those different?
Sparse models are also efficient, but they achieve it differently, often by having tokens only attend to a subset of other tokens. Crucially, though, many sparse models still need to calculate and store the full KV cache for all tokens, even if they don't use all connections. Retention, with its constant memory recurrent RLA, avoids that completely.
Got it. Different paths to efficiency. So looking ahead, what's next for retention or architectures like it?
Well, there's ongoing engineering work, making sure those theoretical speedups, like that 60%, are fully realized in practical deployed inference systems. That's always a challenge.
Bridging the gap from paper to product.
Exactly. Another really exciting direction is the idea of fine-tuning existing large pre-trained full attention models to become retention models.
Oh, so converting existing giants.
Potentially, yes. If you could adapt a huge model like GPT-4 or Claude to use retention, you might get massive efficiency gains without the enormous cost of pre-training a new model from scratch. That could accelerate adoption significantly.
That would be huge. Any open research questions that stand out?
Oh, plenty. What's the optimal mix of local SWA and global RLA-like mechanisms? Maybe it's not every layer. Can we design even better, more parameter-efficient linear or recurrent models to use within these hybrid frameworks? And there's still that fundamental question. Is it ultimately better to sparsely access the full context, like sparse attention, or to compress the context using recurrent methods like RLA? The jury's still out on the absolute best path forward. It's a really active area.
Okay, so to wrap up our deep dive here, retention seems like a genuinely significant step. It lets LLMs handle long contexts much more efficiently, performance-wise and memory-wise.
All thanks to that clever hybrid design, SWA for the local stuff, the innovative residual linear attention for the long-range context, and crucially, achieving this with remarkably small window sizes like 512 tokens.
Yeah, and without adding extra parameters, which is just neat.
It really represents, as we said, a shift in that fundamental efficiency versus performance trade-off in LLM design.
Making these powerful models more practical, more accessible for potentially many more applications.
Exactly. Pushing the boundaries of what AI can do intelligently and efficiently.
It definitely makes you think. Considering retention success at shifting that specific Pareto frontier for LMs, what other big established trade-offs in technology might be just waiting for a similar kind of clever hybrid reevaluation, something to chew on?
Yeah, and just imagining the downstream effects of making powerful AI so much more efficient, the implications for science, for information access, for creativity, it's really exciting to consider.
Indeed. Well, that's all the time we have for this deep dive. We hope this look at retention gave you some valuable insights.
Hope you found it useful.
Until next time.